Hello everybody, welcome to the webinar today. Thank you very much, Peter. We've got quite a lot to cover today actually, and we're really going to only touch upon some of the principles, so consequently following the webinar you'll probably need to have a look through the manual in depth. So I'm going to start off with what we're going to cover today. Firstly, a basic introduction really. This is probably known to a lot of you, but it's really necessary to understand the rest of the webinar. So we're going to go through the analysis methodology behind through how the inputs and outputs work, that kind of thing. Then we'll go on to modeling effects, so understanding how you apply modeling effects in through. And when I say modeling effects, I mean things like modeling a berm, modeling the thermal effects in a slab, looking at the creep within your retaining wall, that kind of thing there. And then using this and with a brief description of EC7, we're going to help you understand how to apply EC7 and through. Also briefly discuss the future developments with regards to EC7 and through. And we're then going to go on to case studies, really understanding the capabilities of the program through case studies, so that you can understand how it's been used in industry. So I'll start with the first section, which is the analysis theory. So what is through and how does it work and what's its methodology? And really through is an embedded retaining wall analysis over the complete construction sequence of a retaining wall. It does stability checks for cantilever and propped walls, so that's a new addition, and it considers the star wall methodology. We've got earth and water pressure calculations at every stage, and it's suitable for sheet piles, secant, contiguous or diaphragm walls. So its development is really based on a paper written by Papin, Simpson and Felton. So this really covers the base analysis methodology. However, it's been developed and undergone continuous development over numerous years. So it start off in version 1, a number of updates within the versions, and now we're on version 19.0. For the numerical representation of through, the wall is modelled as a series of elastic beam elements. The soil to each side of the wall is connected to nodes, and only horizontal forces are transmitted. So in effect, through is basically a soil structural interaction analysis. So it works by initializing the in situ ground stresses. It models the stiffness of the structure and ground, and then movement is generated until the outer balance forces come into equilibrium, and it then checks the stability of the wall, and it looks at the wall load effects and prop forces and calculates them, and then the wall and soil deformations are calculated accordingly. So that's just a rundown, almost step by step, of how through works. Now, the soil stiffness is critical to how the model behaves, and the stiffness matrix is computed by applying loads to the edge of the finite element mesh. And there are two types of soil stiffness matrix. One is the finite element flexibility model, which is a SAFE model, and this basically SAFE has been used to produce the matrix. And the other is the Mindlin flexibility model, where the Mindlin equations have been used to create the stiffness matrix. So in the analysis options you can choose which is the most appropriate, and in the manual there's a detailed breakdown of how these have been derived so that you can look at what's the most appropriate for your problem. Now, is it conservative? We've been often asked by a lot of users, is through conservative, and what are the assumptions that it makes? Well, it does make a number of assumptions. It simplifies the effect of the wall friction. It simplifies the actions of the structural supports, and this is done by treating them as springs fixed at one end, which is a simplification. The initial stages in ground often exhibit higher stiffnesses, but this isn't represented by through because of the linear elastic soil stiffnesses. So it is, however, very difficult to give an estimate of the amount of overprediction, and this is because with each individual problem there's a variability in site and local conditions. So we couldn't maybe put a value on it as such. And in order to look at this, we and Arup and our external customers have done numerous studies, and there's a lot of literature out there to show how it compares. and it's been actually found that it compares reasonably well to other similar types of analysis, and it also compares reasonably well to FE, or finite element analysis. And some of the papers I've listed here, for example, Series C580 shows a comparison of a through analysis, and also there's a paper by Rocco which looks at the through analysis done for the Ashford Tunnel box, and it compares the analysis to actual movements on site. So that gives you an idea that, you know, through has been compared extensively to realistic values. So in order to understand how through works, it's quite important that you understand the kind of inputs that go into through, and to understand the accuracy of the inputs that go in. So with the key inputs, the soil strength and stiffness are critical, so you have to think about the long and short term for that. The groundwater and water pressure, so what is groundwater level, what kind of pressures are you applying? The wall stiffness, the EI values in the short and long term. The support stiffnesses, so you have to calculate your props and your anchor stiffnesses. You know, you have to understand your berms and how they're going to affect the problem against slabs. And of course, surcharges and applied loads, what are they, and what stages are they going to go in. So when you're setting up a problem, really with through, before you put anything into through, you really need to understand the geometry, plan the geometry in advance. What are the soil levels, dig levels, prop positions, and this often depends also on the design approach that you're applying, because you might put a factor of safety maybe on the level, or the water, on the soil level or dig level or the water level. The geometry also impacts on the node position. So for example, you wouldn't necessarily put a prop at the same node that you would have a soil switch, and this is because of the way the analysis works, in that props and loads are applied at nodes, soil switches are applied mid-node, and fill excavations are at mid-node, and the toe of the wall extends to node below that specified. So as long as you understand those boundaries, technically you could put the nodes together yourself within the problem. And you can keep the nodes, as long as you keep the nodes approximately equally spaced and place the nodes below the wall, it should work. However, I mean, through now automatically analyzes the nodes, so as long as you have a good understanding of your geometry and apply it in a way that doesn't conflict with those rules with the nodes, you should be able to input a problem. And I'd also like to note here the passive softening can be specified via the analysis data section at the appropriate stages as well. So we'll now go on to our outputs, and graphical and tabular outputs are available on through. You can export your tabular outputs into Excel and analyze them in detail. So for example, if you want to look at specific values of shear or bending moment, if you want to do a comparison analysis, you can actually maybe put some Excel tables together, put some graphs together, and so on and so forth. We can also get a stage-by-stage output and envelope of results, and you can pick a specific stage that you might want the tabular outputs for. So that's all very useful. But I just want to touch upon something with the modeling methods now. And so now that we've looked at the outputs and we've understood how the outputs work, it's really nice for us to have a look at the modeling methods and look into more detail as to what you would do with through. So in summary, there are a number of effects to be modeled. There's undrained to drain transition. There's a modeling of the props, relaxation and creep, modeling of sloping ground, modeling of berms and thermal effects, and also if your problem requires further analysis, if for example you're looking at seepage, maybe you're looking at a tunnel close by, if you're looking at that kind of thing, then you would probably want to look in maybe into 2D finite element analysis. So we've now developed something called the through safe link, whereby once you've created your problem in through and analyzed it, and maybe realize that you need to do some further analysis, through can actually export some of that, some of the stuff that you've already put in, and set up a model in safe where you have your construction sequence set up, you have your mesh generator and everything else, and you just need to do a few checks within the model and run it. So I'm now going to go on to the undrained to drain transition. And there's a specific sequence that has to be followed with the undrained to drain transition. And in this sequence, you initialize the stresses with the drain material. You switch to the undrained soil, so you set the pore pressures and you switch to the undrained soil. So you model the sequence. You apply the estimated undrained pore pressure profile to the undrained materials where there's no movement. You switch to the drain parameters, again, where there's no movement, and you switch to long-term pore pressures. Now, this is quite a long manual sequence, but Fru now calculates the undrained pore pressure profile for you. So, for example, based on either a more Coulomb model or a modified Cam-Clay model, Fru will look at the stress path and it would calculate the undrained pore pressure. And this feature is actually available through the materials table. So if you have a look at the bottom, it's quite small, but through the materials table you can see that specifically for an undrained material we've assigned a drained material, and this is from this drained material the effective stress parameters are taken. So if we look at the graph here, this is for the more Coulomb model. You can see there's a blue line here, and in the blue line at the top we've got stress paths taken. Along the stress path we've got the effective stress and total stress taken, and so once you've got the final total stress and the final effective stress, the undrained pore pressure is the difference between both. So that gives you a basis of understanding as to how the undrained pore pressure is calculated within Fru. So now that you understand that, you can probably just go and apply it within Fru as an extra stage to get the undrained to drain transition. So modeling of props. Props can be modeled in Fru, and it depends on the type of prop, or for example a moment restraint or moment, as to how you model it. So for example, if you've got a pre-stress, you have pre-stresses, you apply a pre-stress through no stiffness and an applied force. And if you've got a prop with stiffness, you basically use it as a spring, so you apply some specific stiffness or K value. And to apply a moment restraint, you apply with a spring with a 90-degree angle over a 1 meter lever arm. But if you want to apply a moment, you apply a force with a 90-degree angle over a 1 meter lever arm. So there's a number of different ways of applying struts, for example, and this kind of breaks it down a little for you. Relaxation and creep. Now, creep of a concrete structure. Structural engineers often represent this by a change in Young's modulus, but it can't be represented so simply in Fru. And the reason for this is that Fru uses tangent modulus as its basis really, and simply changing E doesn't have the effect that you would want. So if you simply just change your value of Young's modulus here, you're following a line from A to D, and you're not necessarily following the line that you want to follow for creep from A to C. So as you can see, the line that you're following as you increase your E value, the red line shown here, is not the line that you would want to follow. You would want to follow the line as shown now from A to C. And the way to do that is actually to go through an alternate path. So instead of following A to C, you go down, you have a relaxation state from A to B, and then you apply your change in Young's modulus, and then your long-term stiffness, as you can see, it follows the same path from A to B to C, is much the same as A to C. So as you go down now, I can show you with the wall relaxation how that works. So the wall relaxation is specified in the analysis data section. The wall EI value and stress in the wall is reduced by a specified percentage. So for example, if you have a change in Young's modulus, say from 20 to 30, you can actually calculate the wall relaxation from that change, and that's given in detail in the manual. So once you've applied the wall relaxation, you follow the path from A to B, and the system is then out of equilibrium. So once you change your E value, it has to move from B to C, so it follows the same path as creep. So that's how creep is modeled in Fru. And a similar effect is required for props, but it's not automatic. So for example, at the node where you have your prop happens, initially you have two props in the short term, and the two props will be for the value of the short term, for the short term, and then once you take away a prop, you get your long-term value. So for example, your K value. In the short term, you would have a K over 2 value, maybe if it's just half the value. And in the long term, if you're just reducing it by a percentage of 50%, you would just take away one of those props and you would get your long-term struct value. So now often behind a retaining wall you might have sloping ground. So how do you model that? Well, as you would imagine, when you've got a sloping ground, you can use surcharge to model that sloping ground. But a note of caution here is that you do need to include a lateral force at the top of the wall, and that's because if you consider the sloping ground, a lateral force does occur, so that needs to be calculated and applied almost as a strut at the top of the wall. So that's how you would model sloping ground. A question often asked from us is, how do you model berms? And I know there is some guidance given on this in Series C580, but there's a simplified method also given in the FRU manual, which tells you how to calculate or how to represent your berm, basically by in the soil above the base level of the berm, having a modified value of Kp, and then applying a surcharge again along the line of the base of the berm. However, the elastic effect of excavation is modelled, but the berm weight doesn't contribute to the passive resistance in soil beneath the berm. And this is covered actually in more detail in the module in the manual, and you should probably have a look there as well to understand this better. But there is a way of countering this, and that is by reducing the surcharge shown on your right, reducing the level of surcharge slightly below the level of the base of the berm. But you should really read the manual to understand this in more detail. And if that's not adequate, if you feel the detail in that isn't adequate, there is a rigorous method based on calculating revised values of Kp using the method of slices. Now, the rigorous method again is covered in detail in the FRU manual, and you can cover that. And we've done a lot of sensitivity analysis between the simplified method and the rigorous method, and we found that in simple cases, in smaller berms, for example, they do actually compare very well. And if you do have an extensive berm or a very large berm, you should have maybe carry out a sensitivity analysis on one of the berms. So how would you model thermal effects in FRU? Now, the expansion and contraction of slabs and props due to temperature effects can actually have significant consequences. And the effect is effectively an applied strain. So as you can see, there's the equation here showing the value, the way you would calculate the applied strain based on the thermal coefficient of expansion. And you would apply this in FRU using a fixed end force, so effectively applying it through a strut. So if the wall is rigid, you would have an applied force of delta P, and calculate it accordingly from the fixed end force calculation. But if the wall is flexible, you set the force to 0, and you would apply a displacement in FRU, delta L. So it really depends on the type of wall that you have as to what you're going to put in. But you can model the prop, you can model the thermal effect as a prop with a stiffness and a pre-stress. And you do need an additional prop, which is basically an equilibrium force from the previous stage. Now, I have to note here that none of these particularly model soil ratcheting of integral bridges, and that has to be something that you have to consider when you're carrying out your analysis. But that brings me to the end of presenting the modeling methods and modeling of common effects in retaining walls. And I'm now going to move on, as I previously suggested, to what would happen if all this wasn't maybe adequate. Maybe you needed to do a seepage analysis. Maybe you want to have a look at the settlement profile nearby, or have a look at the impact of your retaining wall on a tunnel, or look at the impact of a newly constructed tunnel on your retaining wall. So what would you do with all these things? You would probably consider using something like 2D FE analysis. And for that reason, Oasys has set up a FRU-safe link. So what you would do is you would have your FRU problem, you would run it as you usually do, and then realize maybe that you need to do further analysis. And you would set up the FRU-safe link, and what this would enable you to do is to run a 2D finite element analysis. Now, a quick introduction to SAFE is that it's been developed over 20 years with Arab geotechnics. It's a 2D FE analysis using quadrilateral elements. It carries out plane strain, plane stress, and axisymmetric analysis. It calculates displacements, strains and stresses, and special features which show a more advanced analysis than FRU, features such as time-dependent consolidation, steady-state seepage, cyclic loading, jointed rock model, the application of soil reinforcement, specific material models such as the brick model, and extensive output options. So the way the FRU-safe link works in FRU is actually described in detail in the manual. But to touch upon it, there's a link wizard, and you go into the wizard. It'll give you warnings about what may not be the same, what needs to be checked. It'll then export a GWA, and what the GWA file will do is it will create a save file, and the save file is shown here in the bottom. So what it'll do is it'll create a save file, and it'll create a save file through a number of stages. So, the application of EC7. Now, we've had a lot of questions through about how EC7 will be applied in FRU, and there's been many queries regarding this. So, I'm going to start off. For those who are not familiar with EC7 with a quick introduction. And EC7 or Eurocode 7 is a code for limit state geotechnical design. It's extensive and requires quite a lot of reading, but it basically applies the limit state design through partial factors, and these partial factors are applied to actions, characteristic material properties and characteristic resistances, and tolerances which are applied to characteristic geometries, and the strength and stability should be verified, which is very important. So here I've just got a cut really of the section which is applicable to retaining walls, which then impacts on FRU, and that's section 9 of EC7. And if we go into it, we can see in detail that it's given its definition of an embedded wall, and that's really what we're analyzing using FRU. So, actions for embedded retaining walls. EC7 applies partial factors on actions as well as material factors. And for embedded retaining walls, these actions are described in detail in EC7, and they're summarized as this: well, the weight of backfill material, surcharges, the weight of water, wave and ice forces, seepage forces, collision forces, and temperature effects. It's given in a little detail in the slide. So the design approaches use a combination of partial factors, and these are applied to your design, and they're applied to your actions as well. So right now in FRU, the user actually factors these actions. So it's your responsibility, or it's up to you as to how you would factor them. So within the United Kingdom, we generally use design approach 1. But outside the UK, in mainland Europe and Ireland, design approach 2 and 3 is often used. And for your specific country, you would probably want to refer to the national annex to see which is the most applicable to your country. But I'm just going to focus on design approach 1 as an example here, and you can probably transfer whatever I say to the other design approaches as appropriate. But here, for example, in Eurocode 7, in section 2, they give a detailed breakdown of the design approaches and the combinations of partial factors required. So within design approach 1, you've got 2 combinations of partial factors. It's combination 1 and combination 2. So combination 1 and 2 are covered here, and you can see it from the excerpt from EC7. So with the design approaches for design approach 1, the partial factors on materials actually included and incorporated into FRU. For resistances, this really applies much more to, for example, piles and things like that, so it's not so applicable in FRU. But for a retaining wall analysis, you would really consider the action factors and the material factors. So seeing the material factors already included in FRU, I'm really going to focus on actions in this presentation. So the partial factors on actions, there are different types of actions. There are permanent actions and variable actions, and the actual actions are unfavorable or favorable. And there's been a lot of debate in this area as to what actions, what factors should be applied on what actions and how, and that's often where the confusion occurs. So I'm just going to go back to a through analysis just to get you in that frame of mind. And if you were going to, for example, apply EC7 and through, you would run your analysis as you would expect, in that you would establish your design geometry, your excavation levels and strut levels, and look at what EC7 might say about that. Identify your actions, which are critical, so surcharges, vertical loads and horizontal loads. Identify your analysis stages and determine the length required for rotational stability from star wall. And also, as advised by EC7, you really need to consider your undrained and drained behavior, and also the thermal effects in the props, which I've previously covered in the modeling section. So the passive pressures are treated the same as active pressures, and that is that there's that they are an unfavorable action. Now, there's been a lot of discussion about this in the past, and there has been papers discussing this, saying that passive pressures might be a favorable action, or resistance, for example. But we've discussed this, and we were looking at how the Arup engineers have interpreted it, and what has been said is that really the passive pressures and the active pressures are coming from a single source, and that single source is gravity. So the gravities drive the earth pressure, and the earth pressures are then causing the passive and active pressures. So the passive and active pressures are unfavorable. So that's a description in brief of the single source principle. So the soil parameters need to be considered with the design approach, and as I've mentioned, you can now input characteristic strengths and apply partial factors into through. So you can apply your EC7 factors according to the 2004 guidance. So typically you would start by running a factored and unfactored analysis. So you've got design approach 1, combination 1, and design approach 1, combination 2. So this is for the ULS analysis. You would, within the United Kingdom, if you were using design approach 1 and designing a retaining wall, you would probably start with a design approach 1, combination 2. And that's because this affects the stability of the wall. And it also gives the design values for bending moment and shear force. And then with the design approach 1, as well as applying the factors on your actions, you would also apply the material factors on your soil properties. But it is important and it's critical to look at design approach 1, combination 1, and the reason for this is because it might be critical for structural effects. So for the case of design approach 1, combination 1, you would apply your factor of 1.1 to the input variable loads, and then you would multiply the load effects from the output by 1.35. So the 1.11 really comes from a division of 1.5 over 1.35, which is a combination of, as you can see here, it's a combination of the 1.35 and 1.5 from A1, which is combination 1. As you can see, it's a combination of the unfavorable, permanent and variable action factors. So that's where the 1.11 comes from. And then afterwards, once you've got your outputs, you would multiply your load effects by 1.35. So once you've done this, you would run an SLS analysis. So through will calculate the movements, and we would advise you really to validate this against case studies and look at how it compares. So really we have to note here that geometry effects must be amended manually. So through will calculate the earth pressure coefficients based on, and through will also calculate the earth pressure coefficients based on EC7, but you need to choose your wall friction and adhesion carefully. So those are just notes as an extra. So as well as applying your partial factors, be aware of this. So with EC7, as you can see, there's quite a lot of interpretation to be had, and there's quite a lot to understand. So we have looked into developing through with EC7, and I'll be discussing that in a webinar coming up in the summer. But really, the way we're doing that is that we're rearranging the partial factors currently offered according to your design approach and guiding you along in that area. We're also offering the partial factors for actions. So, for example, you could either choose A1 as a set of partial factors or A2, and it would apply it appropriately to your actions. And also, currently, the EC7 partial factors don't apply to star wall, which is the limit equilibrium analysis within through. but we will be changing that with our EC7 update. So that's all coming in the summer, and watch this space really for that webinar. So I'm just going to give you a quick run through of Fru 19.0 and recent updates in that area. And the first update is the model wizard, which helps you set up your problem, and it gives you something to start with, because initially what you had to do was go into the gateway, input all your values, and then eventually get a graphical input. But now with the model wizard, you input everything so that you have an initial stage, and then you can go through your graphical input section and start inputting your dig and putting your props in accordingly and everything else. So it's very useful, and really the best way to familiarize yourself with this is to go through previous webinars, and also have a look at the online tutorials which are available on the website on the Fru page. Other new updates with Fru 19.0 is that the data entry is by level and not by node. So I think I previously mentioned this, in that you've got your geometry, you input all your levels, you input your problem in, and you don't so much need to worry about your nodes, as long as you understand what's going on in the background. You've got your automatic node creation, therefore, and if you wanted to override it, you could. It now includes a star wall stability check. So what you do is you run your star wall stability check, and as you can see down here, for every single stage you apply whether it's a fixed earth or free earth problem, and Fru will run the star wall stability check, and you get a toe depth from the stability analysis. So as you can see in this specific picture down here on your left hand side, you will see that we've got a number of different toe depths calculated for different stages, and I've just highlighted the critical toe depth for this problem, which is 37.34. So that is the toe depth that will be taken. That'll see if you go up here, you can see that the toe depth taken here is 37.34. And you can even override that toe depth, and I'll discuss that in more detail soon. So the Fru star wall link, I thought it'll be nice for you to understand a little bit of theory behind star wall and understand what star wall is doing. And really, star wall is different to Fru, in that Fru is a source structural interaction analysis, and star wall is a limit equilibrium method. It checks the stability of the wall for an assumed failure mechanism, and each analysis addresses a single stage. There were a number of changes that had to be made to Fru, but you can choose to compute the required toe level from the stability check rather than have it user specified. So for example, you run your star wall check, you look at your minimum level, and you just use that to run everything in Fru. So it's quite handy and very helpful. Another thing which is new in Fru really is the manual override. We've got the manual override here, which allows for example, if you've automatically set up the nodes but you want to put some nodes in specific areas for any particular reason, you can do that. You've got batch testing, and the batch testing has override of toe level. So as you can see here, you can override your calculated toe level from the star wall section, specify a range of levels, and create multiple Fru files for each toe level. So batch testing has actually been a very handy thing, especially for some of our external users. And what it does is that, say you have a star wall stability check and it gives you a minimum value of toe depth, but you want to understand how your retaining wall is behaving, maybe do a sensitivity check. So what you would do then is you would override the toe level, and you would then specify a range of levels. So say for example you'll put a new toe level in 37, and then you will give a range of levels. So maybe you want to know what's happening if you put the toe level up at 36 and 35 and 34. And then once you go to generate your nodes, Fru will actually create a file, not only the file that you're in, which shows the toe level at 37, it will create a file, a new Fru file, one file for 36 meters OD, one file for 35 meters OD, and one file for 34 meters OD, and that will be created in a folder, and you can then go into these new Fru files, look at the analysis, and look at, say for example, if you do increase your toe level, what happens to your bending moment, what happens to your shear force, how does that affect my envelope. So it really gives you a really good understanding of your problem. So that's why it's such a handy thing, and there's a good demonstration of this again on the online tutorial section of the website, so have a look and see. And an upcoming development in Fru, and again something that we're going to present quite soon really, is the integral bridge analysis. And we're going to have a feature now in Fru and that we're working on, as you can see, which is to give you the capability of doing an integral bridge analysis within Fru according to the Highways Agency Note PD 6694-1. And it's just in testing now, but we've got, as you can see, you've got the integral bridge calculation option here, which you can perform. And once you've done that, you can put your analysis data in. So, for example, your stiffness curve data, it's got all the data according to the Highways Agency Note. So all the integral bridge analysis data. And also it's got the strut modeling of thermal expansion and contraction, so it allows for that as well. So it's really a very exciting new feature, and what I will be doing is in an upcoming webinar we will cover this and show you how to use it and cover it in much more detail. So now, how is Fru used? I mean, a lot of people we've often been asked how is Fru used internally and externally, and you know, and to show really the value of Fru. And I've chosen 3 case studies, and due to our limited time I can only cover them very briefly, but some case studies are available on the website and you can read them in more detail, and case studies will be made available over time. So I'll start with a case study from one of our external customers, which is Van Earl. And this case study was actually presented at the Deep Foundation Institute, and it's a case study showing how novel solutions were modelled for a roll-on, roll-off ramp retaining wall. So I'll introduce you to the problem. It's a contiguous pile retaining wall has been designed. It supports compression, tension, moment and lateral loading from a new bank seat. It accommodates the proposed link span bridge, and there were numerous site constraints within the site here. So solutions that you would normally consider, things like tie-back anchors and temporary propping, were not an option. So this was actually a project carried out in Dublin, and the proposed solution was a novel solution, and the solution was that it was proposed that they would simultaneously excavate both sides of the contiguous wall to 6 meters depth, and then they would construct a 2.5 meter wide concrete counterweight structure behind the wall. So it's a very different kind of problem. It's not a standard retaining wall, but Fru was still able to be used in this problem, and Fru was used to run serviceability analysis. So unfactored surcharge loads and soil were used to estimate the lateral deflection, the bending moments and the shear forces. So if we go through the construction sequence here, you can see they're showing the capping beam construction. It goes on to show the simultaneous excavation of both sides of wall to formation level. And then it analyzes the construction of the counterweight structure. So here's the first layer of the counterweight structure and the completed counterweight structure with loading here, showing here for a moment, loading, there you go. So as you can see, it's quite an interesting analysis. It's very different to a normal standard retaining wall analysis. So I'm now going to go on to a different type of case study, and this is a case study that was carried out within Arab. And this is really a very good demonstration of how Fru can be used in conjunction with a lot of other pieces of software or Oasys software to look at a holistic retaining wall problem. And so I'm just going to start by introducing the problem. Now, this was the construction of the UCL hospital. And the UCL hospital was constructed in a densely populated urban area, and it was running very closely adjacent to a lot of buildings, in particular the Rain Institute. So the section of the retaining wall running alongside the Rain Institute had several restrictions. So one was just the proximity, really, and it was within 300 mil of the Rain Institute, and it was very close to the pile cap, as you can see to the left-hand side. But also there were requirements to locate a service lift there, and there were tight space restrictions that had to that went on to affect the wall thickness. So as you can see, it was a very interesting problem. And for this problem, in order not to undermine the basement of the adjacent Rain Institute building, it was proposed that the capping beam over the section of wall be raised above the new lower ground floor basement level. So this formed an upstand in the final condition, and it was proposed to construct a 600 mm diameter hard soft board secant pile wall with male piles at 750 mm diameter centres, and the smaller diameter of 600 mm in the area was required to be temporarily propped at 2 levels. So as you can see, there's a through run there showing how the analysis was carried out. But the analysis methodology was very interesting. So the iterative solutions were iterative methodology was actually used to calculate the effect of the movements on the Rain Institute piles due to excavation in front of the secant pile wall. And the Arab engineers commented on the compatibility between the software and the gateway system between all these four programs, which enabled the quick changes and convergence. So if we just look at this here, what was done by the Arab engineers was that they started with the through analysis, and out of the through analysis they got the horizontal ground movements, which were applied within ALP on the Rain Institute piles, and then they got the vertical stresses, which were applied within pile to calculate the settlement and look at the settlement analysis. And then the vertical stresses went on to calculate the axial stress. So for example, from pile they got the axial stresses, and from ALP they got the moment, and these were fed into a sectional analysis, and this looked at a section of the pile in ADSEC. So once that section of pile was analysed, the cracked value of EI was used to feed back into ALP, and so it was very iterative in its process, but very interesting analysis. So that's how you would run an overall retaining wall analysis, not only using through, but understanding the transverse loadings, understanding the effect of the settlement of the piles, and understanding the behavior of the pile themselves in a sectional capacity, using all the Oasys piling and retaining wall software. And this is actually covered previously in one of our webinars, which you might want to look at if you're interested. The final case study is of a very high profile building, and this shows an example of how through is regularly being used for deep basement design. So really this could have been a case study for any one of a number of buildings built all over the country, but I'm just going to focus here on the Pinnacle, which is a very current project, and it's the development of a 62-story building in the City of London. The existing basements and ground levels across the site will be deepened, and a new site-wide basement is proposed to be constructed. The proposed building will be founded on a combination of piles founded in the London clay and Thanet sand strata. So through was used to design the hard firm secant pile retaining wall located at the southeast section of the site. The design was carried out in accordance with BS 8002 and Cirrus C580, and so it was carried out for the unfactored soil parameters, so an SLS analysis, and is carried out with factored soil parameters for the ULS analysis, or ultimate limit state analysis. The design methodology for vertical load considers both total and effective stress design. Shaft capacity is only assumed below the excavation level. So for the effective stress design, the input horizontal effective stresses are those calculated from the through retaining wall analysis. So because the wall is carrying vertical loading, wall friction may not be generated on the back of the wall, so therefore no benefit of the wall friction is taken on the active side of the through analysis. So that's why delta is taken to 0 there. So if we go into the analysis and have a look at the construction sequence within the wall that I mentioned, as you can see down to the southeast side, as you can see is highlighted down here with that bright blue line, we've got the wall, and a number of sections were taken through that wall, and the SLS and ULS runs were done for each of those sections. But if we look at one section, for example, I'm just going to run through the construction sequence. So here we've for stage 1, we've installed the wall and constructed the capping beam, excavated and installed the temporary prop, excavated and installed the second temporary prop, excavated to formation level, constructed the basement slab, removed the second temporary prop and construct the ground floor slab, remove this first temporary prop and construct the basement slab. So that gives you a good understanding of what's going on with the construction sequence. So now within through, I think it'll be very interesting for you to see how the analysis was done within the FRU and the kind of results that you're getting. So I've just chosen this one specific section. So I've just chosen this one specific section here, and it's looking at the SLS analysis. So if you look, here's the initial condition, the installation of the wall, the excavation to ground floor slab, the excavation to basement level 2 slab, the excavation to basement level 3 slab, the construction of the slabs in the basement levels, basement level slabs in the ground floor slab, and then the long-term case. So what happens in the long term, and then the drain to undrained transition, or the undrained to drain transition in this case. So in summary, we've covered quite a lot here, and we've covered it very quickly. So we've covered the basic theory behind FRU. We've had a look at the inputs and outputs, and the modelling of effects in FRU, the EC7 limit state analysis, an introduction to it, and how it would be applied in FRU. And then case studies showing how FRU has been used in industry, how it's used for just a general large basement project, and how it's used for non-standard projects. So now what next? After all this, you might be very interested to see what you can do with FRU and how you can use the more advanced modeling analysis, or maybe how you should apply EC7. Well, really you have to understand the FRU methodology, and a better look into the help file and the manual would be useful. Try the step-by-step examples. There are a number of previous webinars which are helpful, and which cover FRU, show how to set up a model in FRU, show the graphical interface of FRU, and there are also, of course, the online tutorials for FRU. And support. The technical FAQs are very handy. They show you a lot of questions that have been asked by previous internal and external customers, and then there are, of course, online training movies. And please feel free to contact us. We're there. We're at the end of an email or at the end of a call. So please do call us if you have any queries or questions, or want to understand how to better use FRU. So it leaves me now to say thank you very much for listening. I realize we covered a lot in a short time, so I appreciate your attentiveness. And are there any questions?